So welcome to the LPL evening lecture series. So this evening's speaker is Dr. Shane Byrne. If you Google Shane Byrne, you might come across a Shane Byrne, the motorcycle racer, that goes by the nickname Shaky, or a professional rugby player, Shane Byrne. So I've known Shane since 2012 when I came here and I was his PhD student. I've since... there's also the Canadian psychic Shane Byrne, and they have exchanged information and had some chats. So there's a lot of Shane Byrnes out there. I've known Shane for 7 years now. He was my PhD advisor, and now we continue to work together and collaborate. And so as far as I know, I think this is Shane Byrne, the scientist, but maybe he's taking a secret break from his professional motorcycle racing duties to be here with us tonight. But this Shane Byrne is a professor here in the Lunar and Planetary Lab, Department of Planetary Sciences here at the University of Arizona. He's originally from a small village in Ireland and moved to the United States in 1998 to attend Caltech for grad school, where he got his PhD. He then worked at MIT and the U.S. Geological Survey up in Flagstaff before coming to the University of Arizona to join the faculty in 2007. He's the member of several spacecraft teams for both NASA and the European Space Agency. He's the director of the Space Imagery Center here at LPL, and he's also currently the assistant department head. He mostly studies the surfaces of planets in our solar system, especially those relating to ice processes. And tonight he's going to be talking to us about ice cores and climate on an alien world. So welcome, Shane.
Thanks, Ali. It sounds like everyone can hear me. This looks like it's working. Let me try and get my slides started here. Yes, I've been very fortunate to end up in a career where I do things as outrageous sounding as being a Canadian psychic. But like getting to fly these spacecraft around the solar system and try to figure out things about other planets is a great privilege. Oh dear, I hope this window is... Let's just do that so it doesn't bother us. Okay, so today we're going to talk about the ice record that we have of climate on an alien world, and that alien world is Mars. Here on the front page, or on the cover slide, we have a picture of the North Pole of Mars, which is right around here, and it's got this giant polar ice cap on it here. You'll also see a lot of familiar looking things off to the left as well. We've got cloud belts here and an atmosphere that you can sort of see at the limb of the planet. So in a lot of ways, Mars is pretty close to the Earth, but then it's exotic in other ways as well, which makes it kind of interesting to study. One of the reasons, or one of the things that I find most compelling about Mars, excuse me a second, is that I think climate change on terrestrial planets is a big deal, especially for us here on the Earth at the moment. And Mars offers a way to try and understand the impacts of different ways of forcing our climate that is potentially a tractable problem compared to what we do on the Earth. So on the Earth, we've got all sorts of complications like oceans and vegetation and people and all sorts of things that are affecting the climate in ways that are very difficult to understand, and the Earth is replete with all these feedback mechanisms that make things very complicated. But on Mars, it's a lot simpler, which doesn't mean it's simple, but it's a lot simpler to understand. It's really just a thin atmosphere with sunlight coming in and heating it from below, a lot like arid regions on the Earth. And we don't have any, or we don't have much, at least, of any melting of water ice. It's all just transitions between vapor and solid. So it's easier to predict how water ice is going to move around and where it's going to condense and so on. Despite the simple nature of the Martian climate, it's got a lot in common with the Earth. So it also has these ice caps that we talked about at the pole, kind of similar to the Greenland ice sheet that we have here on Earth. There's lots of surface processes going on in these ice sheets, melting on the Earth, but mostly just sublimation, which is just ice going directly into gas on Mars. And then, most of all, though, and what we'll talk a lot about today, are these layers within the ice sheets. So this is Greenland here, with lots of layers detected by radar instruments and ice cores that we drill straight through this to actually study these layers and what it means for climate history. And on Mars, we have radar instruments, which you can see straight away are coarser in resolution, but which also show layers within these big ice sheets within the polar deposits. Another reason why Mars, I think, is compelling to study is that it's going to be an archetype for a type of extrasolar planet of which we're on the verge of discovering thousands. So we're here, one small speck off in the outer regions, the suburbs of the Milky Way here. And we already know about over 1,000 extrasolar planets. They're all sort of in our local neighborhood for the most part. It's very hard to find planets that are further away. This shows some of the extrasolar planets that we've already discovered. Along the bottom here are the distance from the star, and along the y-axis here is the size of the planet, like the physical diameter of the planet. So for big planets, like stuff up at the top here, you can find them at almost any distance from the star. But for planets close in, you can find them at almost any size. But over here, it's kind of hard, or has been hard, to find these planets. So we don't really have a lot of Earth and Mars-like planets at that distance from their stars. So things that would share a climate similar to our own. That's about to change in the next couple of years. We're about to build space missions that will literally detect thousands of planets that are in this area here. We know they're probably there, it's just that we don't have the means to detect them right now. So Mars is going to become an important analog for these other planets, and a way that we can try and predict what their climates are going to be like. Earth could do the same, but then Earth is possibly very special, right? Because it has biology and all these other complicating factors that I mentioned going on, which are maybe less likely on other planets. So having both Earth and Mars together really allows us to study what will eventually be thousands of other examples. So Mars can hopefully form the link between those extrasolar planets and the Earth that we study so well. So on Earth we have, as I said, radar detections of layers. This is Greenland again here, and ice cores that we drill through these. So this is a borehole of one, but this goes down maybe about 2 miles into the ice. So we pull out these cores in sections, we slice them up thinly, we do analysis on it, and then we can figure out what climate has done on the Earth. So this gives you an idea of CO2 concentrations over time. So here we are at the present, and this goes back 650,000 years. On Mars, we may be able to go back more like 5 or 6 million years into the climate history of the planet, because the ice is probably older there. So you can see we've kind of come in and out of glacial periods here on the Earth. The blue is where we've been in glacial or snowball type period, and the yellows are where the interglacials are, the most recent of which has allowed us to evolve and move out of Africa and colonize the world. The tiny little sliver that you can barely see on the right-hand side that spikes up above the level of this plot is what we've done just in the last 100 years or so. Okay, so since we'll do a lot of comparison of Earth and Mars here, I thought I'd start with some brief facts to just give you an idea of what Mars is like compared to the Earth. It's actually very Earth-like in a lot of ways. So it has a size that's close to that of the Earth, about half that of the Earth, and the mass is a little over 10% of that. The solar distance is not astonishingly different, so it's about 50% further from the Sun than the Earth, so not like the outer solar system at all, very similar to the Earth. It has a similar year, almost 2 Earth years, and crucially for the climate, it has a similar obliquity, and this is how tilted over the planet is. It has a similar length of day, so 24 hours and 37 minutes instead of just 24 hours. And it has a lot of similar stuff on the surface, in that it has the same rocks you'll find here on the Earth, the same water ice you'll find here on the Earth, a lot of the same geologic processes and so on. It has 1 or 2 exotic components. You can find carbon dioxide ice on Mars, and you don't really find that naturally on the Earth. But for the most part, it's a very Earth-like world. There are some differences. The atmosphere is the biggest one, where on Mars it's super low pressure, just about 0.006 bars, so that's about less than 1% of that of the Earth. It's mostly carbon dioxide instead of the nitrogen and oxygen we have here at the Earth, and it's much colder than the Earth. And the water, or the clouds that you see here, are all water ice crystals rather than water droplets that we have on the Earth. But even in spite of those differences, the climate still works in a very similar way. We have sunlight, like I said, coming in, just heating, or coming through a transparent atmosphere, heating the surface, and that drives all the dynamics of the planet. So we can apply our knowledge of how the Earth's climate and weather works to Mars, and it works out pretty well. The same models can be used for both planets. Okay, so why do people care about Mars? Geologists love it because it's got a low gravity environment, but we can still test all of our geologic processes to see if they work on familiar materials, familiar rocks. Mars also preserves surfaces from every part in its history. So on Earth, we only really see rocks from the very most recent parts of Earth's history. Plate tectonics does an efficient job of recycling most of it. But Mars has rocks that are 4 billion years old, and it has rocks that formed just a few 100,000 years old, or tens of thousands of years old. And it also has about the same land area as the Earth. So a lot of Earth is not studyable by geologists. It's all under oceans at the moment. But the continental area of the Earth is roughly the same as the total area on Mars. So there's a lot to study here. Climate scientists also love Mars because the atmosphere is Earth-like, but it's simpler. So we can really test our climate models and meteorological models to see if they behave correctly in a Mars-type environment. So it's different enough to kind of stretch ourselves, but not so different that there's no hope of understanding it at all. So the data that I'll show today come from the Mars Reconnaissance Orbiter, which is a spacecraft that launched in 2005. The launch allowed us to take this 9-month cruise to Mars. So we basically transfer from the Earth at a specific time that allows us to sort of catch up with Mars in the lowest energy kind of way. After arriving at Mars, we do this capture around Mars, so we rely on Mars's gravity and a burn from the spacecraft there to put us in this very elliptical orbit, and we trim that orbit down over time by basically dipping these solar panels into the atmosphere. So every time we do a close pass by Mars, we dip the solar panels into the atmosphere and we aerobrake. So this sounds risky, and it is. Back in the 1990s, we lost one spacecraft doing that. The reasons were somewhat embarrassing. It was a mix-up between meters and feet, that kind of unit confusion that you usually give 0 points to for college students on homeworks. But unfortunately, it happened between JPL and Lockheed Martin this time, so there was no way for them to retake the test. MRO is a pretty large spacecraft compared to its predecessors, so we have just with an engineer for scale here, Mars Global Surveyor, Mars Odyssey, and Mars Reconnaissance Orbiter, the star of the show. What really allows us to return the huge amounts of data that we've been able to from MRO is this thing up here. It's kind of the unsung hero of the whole story. Is this giant antenna, which is 3 meters across, and allows us to return the high-resolution images that we acquire. Otherwise, we would just never be able to send an instrument like the Highrise Camera, for example. There's a whole set of instruments here that I won't really talk much about, but 2 that will appear consistently are Highrise, and I'm on the Highrise team, which is operated here out of the University of Arizona, so I'll focus mostly on that. But the Sherrod instrument, which is a ground-penetrating radar, is also very important for the study of these ice cores, just as it is in Greenland. Okay, so there we go. Highrise Camera then works by basically having this set of sensors that it sweeps across the surface. So we have the spacecraft that's in orbit around Mars, and it's looking straight down. And we rely on that spacecraft motion to essentially like sweep ourselves across the surface, and we build up an image 1 line at a time. So a high-rise image is really more like 40,000 images, each image being 1 line across, and we stack all those little images together to form a big one. The instrument itself is enormous. The telescope is about 0.5 meter across, so about this big, and instead of pointing up at the stars, we just point straight down at the ground. It's the most powerful camera to fly to another planet. Obviously here on the Earth we've got all sorts of people looking at us every day with much more powerful cameras to figure out what everybody is doing. But as far as planets, telescopes that go to other planets, this has been the largest one. This allows us to take images that are very high resolution. So we have images which on the ground have pixel sizes of about 25 centimeters, which is about this big. So we can see things the size of a beach ball or so on the surface of Mars. And we can plant this camera pretty much anywhere, and we can get an image of the surface of Mars within 2 weeks or so of any spot we like. So that has allowed us to both investigate all the interesting spots around Mars, but also to repeat image lots of places to look for change over the years. Just to give you an idea of how much data has been returned, as of this afternoon, when I inputted these numbers, we have close to 64,000 Mars images returned, tens of thousands of billions of pixels. But this only covers about 3.5% of the surface of Mars. So it's a very carefully chosen 3.5%. So we're not taking pictures of like the equivalent of Kansas or anything. You know, sorry to people from Kansas, but it's more like we're looking for things like the Grand Canyon. And so we choose very carefully where we want to point this thing, and it's not like a random sampling at all. So this 3.5% is also kind of an upper limit, because many of these images, like I said, we're looking for changes, so we want to image the same place over and over, and the 3.5% just assumes that it's all unique coverage, which it isn't. Also, of note is the number of stereo pairs that we've completed. So stereo images involve taking 2 images of the same spot from different angles, and then we can reconstruct the 3D nature of the topography from that. So your eyes and brain do this about 10 times a second, you know, every time you're awake, for the whole time that you're awake. So your brain's a pretty powerful supercomputer. For us, to take those 2 images takes months to plan them. And then it takes maybe a week of human and computational time to turn that into a model. So, or a height model rather. So your brain is extraordinarily efficient compared to what we're doing at Mars. But just to be able to do this at another planet is pretty neat. Okay, all of the images I'll show are also color enhanced. So this is what Mars would look like if you were in orbit and looking with your unassisted eye at the surface. It's pretty bland. There's not a lot of contrast and not a lot of color differences from place to place. So we enhance the images so that it turns into something more like this, where you can see the contrast by basically stretching out the dark and light tones to be at the full spectrum of what you can see, and also enhancing the color. So we do that contrast stretching for every different color band we have, so that the color differences really pop out as well. So although you will see lots of beautiful high-rise images that look very colorful, for the most part, Mars is a little drab if you were to look at it from just with your naked eye. So some of the colors that we get are actually really spectacular. So this is one area called Lily Fossey, which is especially good for different types or different diversity of rocks. We have these bluish material, which is probably just volcanic rock that hasn't really been weathered much. And then we have other stuff like this reddish material or this cyan material, which is really ancient and modified volcanic rock that's been changed a lot chemically over time. As well as Mars, we occasionally point up and take pictures of Phobos. So this is a moon around Mars as well, and just shows off the abilities of the camera to get high-resolution images and pretty colors as well. Okay, so just to give you an idea of what you're actually able to see at 25 centimeters per pixel, here's a couple of things that are at least sort of understandable on a human scale. So you've probably all seen pictures of the Mars rover Opportunity. This is some tracks that Opportunity left, or this might be Spirit actually, but Spirit and Opportunity are kind of identical rovers. So these are tracks that the rover has left in the dirt as pictured from the rover. And if you look at that from orbit, you can just about see this white line is doubled up here. It looks like it's a little out of focus, but actually we can see both of the wheel tracks from that rover. More to the point for us as scientists, though, is that we can see the layers and the rocks here that we're so interested in, which the rover can also see. But we can do this anywhere on the planet, and the rover just has one landing site. Other things that you may remember, the Pathfinder landing from the 1990s. where we had this cute little rover called Sojourner that drove around investigating things, including this rock called Yogi. I'm sorry, that label is moved. It should be up here. And in the high-rise image of the Pathfinder lander, you can see Yogi, that little rock there. So a rock that size sort of looks like, you know, this big on Mars. We also do some dynamic shots as well. So this is the Phoenix lander coming into land. You can just about see it here, this tiny little bleb. If you blow it up, it's the Phoenix lander on its parachute coming in towards the surface. It looks like it's about to fall into this giant crater and be lost forever, but that's just because the crater's kind of in the background. The perspective looks a little like this. The lander came down safely in front of the crater here. Once on the surface as well, we can see what that what the lander looks like, and this has sort of become a standard thing that we like to do for NASA missions now, because everybody wants, one, to make sure that everything is working properly during the descent, although there's actually not much we can do about it if there isn't. But also to, if something does go wrong, to be able to sort of reconstruct that afterwards and figure out what went awry. So the lander itself looked like that, and you can kind of see this up here and blown up on the right, the two solar panels sticking out. The other hardware that we're littering the surface of Mars with, there's the parachute and the back shell, and then the heat shield over here, etc. There are larger landers than this that have gone down, like so the Curiosity rover, for example, had a heat shield that was bigger than the Apollo re-entry vehicle. So back in the 60s, they were able to fit 3 humans and all the equipment they needed behind this thing, and now we're just you know, got 1 rover behind it. But the heat shield is so large that we were able, and the parachute, that we were able to take pretty detailed pictures of that. So here it is on its descent toward the Martian surface. And here it is on the Martian surface. So the heat shield back shell just impacts the surface, and the parachute actually just blows around in the wind. So you can kind of see it in a series of images here, just being moving around. Within a year, this will be covered with dust, and it'll be almost impossible to see. One other application of Highrise that's just based on other spacecraft is helping with their operations. So Curiosity, this rover that I just mentioned, has to drive a long way from its landing site toward its main target, which is to study layers in this mound in a crater. Unfortunately, they discovered that driving over this hard rock does a lot of damage to its wheels. So they needed to replan the route to go over soft sand-like material instead of trying to drive across the bedrock. But you can't see much when you're down on the ground and you're looking around trying to find your way or pick your way around these rocks. So we use high-rise images to plan out the route of the rover and to get it from A to B with a minimum of damage to the wheels. So there's another rover going in 2020, and they have apparently fixed this problem, so we won't have wheels that are falling apart anymore. Okay, so just a few other things to give you an idea of the resolution of the camera. So here are some lava-colored plains on Mars, which we can zoom in on and continue to zoom in on and continue to zoom in on until eventually we see these interesting lava swirl-like features. So we can go from multiple kilometers down to looking at things that are only a few meters across. In terms of climate records, we can see layers in some of these mid-latitude craters or equatorial craters showing climate changes that from billions of years ago. So this is kind of like Camp Verde, if you've ever been to Camp Verde or driven through it. So it's basically like an ancient lake bed that's been eroded by the Verde River that's flowing through the Verde Valley now. And so you can see sequences of layers from lake deposits there. And that's what we're seeing on Mars here. These craters were filled up with lakes and eroded away. Those lake deposits were eroded away later to show these layers. Being at Mars for a long time, we can see things change on the surface too. So this is a dune field near the North Pole of Mars. And if we look at different times of the MRO mission, you can see these dunes move. So here's a sand dune. It's moving from right to left here. And this was thought to be impossible before the MRO mission actually flew. We thought that wind speeds never get high enough to move sand on Mars, according to theory that was based on Earth-like dunes. And then, of course, Mars had the real answer, which was that we were wrong. And that has led to like a revisement of the theory of how sand dunes move that is applied to Earth now as well. So the value of studying Mars is that we can test all of our assumptions in different situations like this. We can also see these mysterious streaks extend downhill, which may be due to liquid water or maybe due to dry material flowing down the slope. It's still being argued about right now. But these occur on the hottest slopes on Mars, and they seem to extend downhill during the summer at the hottest times of year and then disappear again in the winter and reoccur the following year. There's polar ice changes on Mars too. Some of these features within the carbon dioxide ice expand by meters per year. So this is a pit that started off about 200 meters in size and has been growing by 3 or 4 meters every year since we've started to observe it. And then we also just see like static features appear where none were before. So new impact craters are occurring on Mars, and we've cataloged about like close to 1,000, I think, new impacts now. And so that is allowing us to figure out what the impact rate is on Mars, and we can figure out from that how old different terrains are by counting up craters and using that rate. MRO, by looking over long periods of time, is really helping us understand a lot about every aspect of Mars. Okay, so just a little bit more about the stereo, because it's kind of central to the rest of the talk. We get stereo on Mars from looking at the same point on the ground from 2 different angles, and our base here could be tens of miles apart. So the spacecraft is in very different locations, but looking down, rolling towards the same spot on the surface, and that generates a little bit of parallax because of the different directions. So like I said, you can do this 10 times a second without even thinking about it, but it takes us like about a week to take 2 high-rise images and turn it into 1 DTM, which is a map of the height here of the surface. But once we do that, there's lots of great things we can do with it. We can generate these perspective views, so you can actually, without having a rover, simulate what you would see if you were standing on the surface here. So this is a mound near the equator of Mars that has all sorts of nice debris fans coming out of it. There's layered deposits within canyons in Valles Marineris that we can map out from these perspective views and create all these geologic maps that tell us about how things have varied over the years. We can also produce these fly-through movies, which gives you, well, a pretty product to begin with, but also allows you to figure out a lot about how things are arranged relative to each other. So it's interesting, these pits here are caused by melt from this impact event, devolatilizing ice in the subsurface. This is Mojave Crater on Mars. So we've got great data sets and this fantastic spacecraft that's produced them, so we can start to apply them to all sorts of problems. And like I said, the ice and its behavior on Mars is both familiar and exotic. There's some exotic elements like the carbon dioxide ice. And carbon dioxide ice can do lots of amazing things on Mars. It can sinter into these transparent slabs and then get heated from underneath. So we have geysers of carbon dioxide and dirt being thrown into the air from that. We can take pictures of these, or the aftermath of these geysers, at least with Highrise. These are geysers at these little points here and the dirt fans that you can see being thrown out here. There's also avalanches in progress. So this is a steep cliff near the North Pole of Mars where CO2 and probably a lot of dust and chunks of water ice from the scarp face are avalanching down here. And you could kind of ask yourself the question, if I were to take a random picture of a mountain range on the Earth, what are the odds that I would see an avalanche in progress? And the odds are very slim, right? But this particular cliff, at one time of year in the spring, every time we fly over it, we take a picture, and 50% of those pictures have avalanches that are in progress in them. So this is a crazy active place. And you can imagine maybe setting up a viewing platform here and charging admission maybe in the future, or at least that's my dream. But if you were standing here, you would just see these avalanches coming down almost one after the other with no gaps in between them, because half of the time there's an avalanche happening whenever we take a picture. There's also some weird features on the surface of Mars, like these spiders, and these are caused by these geysers and jets of carbon dioxide gas underneath the ice slab, kind of carving these grooves, and they later get filled in with this bright icy material to highlight them. And there's enough David Bowie references to spiders on Mars in relation to this that it's not really certain what you'll get if you search for this later on Google, but this is a real geologic feature on Mars too. And oh yes, this is another picture of the avalanche, but I just wanted to mention that since the color images we take are at slightly different times, because we use this push broom mode, we take the blue filter first, then we take the red one when the spacecraft has moved a little bit, and then we take the infrared one when the spacecraft has moved a little bit more. When we stack these together into color images, it can cause a little blurring if something is moving, and you might notice there's a little blurring around the edge of this avalanche. So if I just flip through the three bands of the color here, you can see those that avalanche cloud moving just because it's in progress as the spacecraft is flying overhead. And we can figure out its speed from that, so it's moving like pretty fast, like maybe about 20 feet per second or so. Okay, so those are some of the exotic things, but Mars is also very familiar as well in that it has these giant water ice caps with the layers inside of and the climatic information that we're so interested in. And it also has glaciers in the mid-latitude areas. So here's a glacier of water ice that's flowing downhill and emptying out into this valley here. So all quite familiar when you think of Earth-like features and how they compare. These big ice caps at the two poles of Mars, the south and the north poles, are more or less the same size as the Greenland ice sheet on the Earth. So there's 4 large ice sheets in the inner solar system. 2 of them are on Mars and 2 of them are on the Earth. So the north and south poles of Mars, and then Greenland and Antarctica are the 2 big ones on the Earth. And I didn't put Antarctica here because it's bigger than all of the other ones put together, so it's kind of like cheating a bit. But these 3 are pretty comparable to each other. This is a color map showing the elevation here. And just to make it clear, I took a profile through all of these, and there's a profile through Greenland here as well, and just plotted what the elevation looks like. So you can see these ice caps on Mars are about a couple of kilometers thick, more or less the same as they are on Greenland. And just like that radargram on Greenland that showed the internal layers, if you take a radar data that goes across one of these ice sheets on Mars, then you'll see lots of layers in between here. Although much lower resolution than we have for Greenland, so there's kind of limitations in what we can figure out just from the radar data itself. We also get a lot of information on the layers by looking at these troughs here. So these are like windows into the stratigraphy in that they're eroded in and show a section of layering that is close to the surface. So if we were to look at one of those, one of the steeper examples, you would see these layers of water ice here. And then underneath the North Polar Cap, you see these layers of water ice and sand kind of interbedded. So this is from a very different climate period when there was really no ice cap and there was this big sand sea blowing around the North Pole of Mars. So we know that Mars's climate has varied a lot because we can see periods in the geologic record where there was no ice sheet at all. And we can see periods in the geologic record where there is an ice sheet, but things are changing, so the ice is maybe more stable or less stable with time. So what are the things then that cause climate change on Mars? Well, luckily it's much simpler than on the Earth because there's, as mentioned, no people, no vegetation, no oceans, no volcanoes going off and so on. But there are changes in Mars's orbit, and that's mostly because it's closer to Jupiter and Saturn, and they exert this influence over Mars that tugs it around in the solar system. So the things that change on Mars are its obliquity, so this is how tilted the planet is. And today that's very close to the Earth. It's about 25 degrees, whereas Earth is 23.5. But over time, this obliquity or the tilt of the planet goes back and forth quite a lot. So here we are in a low obliquity period when the North Pole is pretty much pointed straight up with respect to the sun. Or here we are in a high obliquity period where the pole is pointed toward the sun. So when the pole's pointed towards the sun, things are warm at the pole and ice is less stable. The shape of the orbit also varies a lot from circular, like the Earth is today, to elliptical, like Mars is today. So it goes back and forth between these states. And then when the orbit is elliptical like this, the entire orbit spins around the sun as well. This takes about 50,000 years for the orbit to spin around. It's one of the things that varies the fastest on Mars. So all of these things influence the climate, and they all influence the amount of sunlight that, that Mars's poles see. So if we were to look back in time, so here's a plot that goes from today at 0 here to 10 million years in the past, and the obliquity has done these big swings. And the green line here shows what the Earth's obliquity has done in the meantime as well. And Earth's obliquity doesn't really change much. So orbital change is not a big factor for the Earth in determining what its climate is going to do. But it's a massive impact on what Mars is going to do here. So we don't change much because we've got this giant moon sitting out to the side, which stabilizes us against gravitational tugs from Jupiter and Saturn. But Mars doesn't have that luxury, so it gets pulled around a lot more. So it goes anywhere from 15 all the way up to like 45 degrees. The eccentricity of the orbit, so how non-circular it is, also goes up and down. And you can put all these things together to figure out how much the amount of sunlight at the North Pole varies. And it varies a lot. It can go from about 150 on this scale up to at least 3 times that, up to 450. So a factor of 3 is quite a lot in determining what your climate's going to be. And it's the difference between the equator, the Earth, and basically the northern edges of Antarctica. So when you think about what a factor of 3 can do on the Earth in terms of changing the climate, then you get an idea of how much the Martian climate has changed throughout history and all these very high frequency up and down motions. So what happens then when these orbital fluctuations happen? Well, ice can get stable, become stable at the poles or unstable depending on what the orbit is doing at any particular point. So when obliquity is high, for example, and the poles receive lots of light, then water ice ablates from the poles and ends up in the mid-latitudes. And then when the obliquity goes back down to low values, then we have the water ice transported back and it freezes back onto the poles. So this back and forth creates a lot of the layering that we see in the polar caps, and also creates layering in the mid-latitude ice. So here's some ice in the mid-latitudes. It's about a cliff that's about 100 meters high here. And if we zoom up with Highrise, and I kind of stretch the heck out of this image to show the colors here, but you can see layering inside this ice in the mid-latitudes too. It's not very well studied at the moment because there are not many places that we can see this with the instruments that we have. But that will change in the future, and there's another big climatic record to be studied in these mid-latitude ice deposits too. For now, we're looking mostly at the poles because it's the easier place to look, and there's 2 real ways we can do this. So we can look at these erosional troughs that I showed before, and we can see all these layers in them. The upside of that is we use Highrise to do it, so it's got very high resolution, and we can see really, really thin layers. The downside is that it only shows like the top 10% of the layers. So the deeper stuff is just not exposed in these troughs. We can also use the Sherrod radar instrument that I mentioned at the beginning of the talk, and they can see all the way through this ice, so they see the shallow and the deep layers. But the downside is that it's pretty coarse resolution. So all of these layers here, for example, from top to bottom here, are basically just sort of like fitting in this section here. So you can see there's just a couple of radar reflections when we know that there are many, many layers. So both of these data sets have their pros and their cons. With the radar data set, people have divided up the polar cap into these big sections. So again, this is about 2 miles of ice here from top to bottom. So these are big individual sections here of the layering. So very coarsely kind of mapped out. And each one of these is basically like an ancient polar cap. So after, like at the beginning, before the polar cap starts forming, this is the topography here. Halfway through its formation, this is the surface. And then a little bit further in time, this is the surface. Until today, we have the current surface up here. So you can put these things together to see what the North Pole looked like without the polar cap. And as the polar cap grows, and these colors are meant to be height again, you can see the polar cap grow into its current shape. And it doesn't grow evenly. It grows in this area off the pole first, and then it kind of spreads around to these other sides of the North Pole. So as well as the radar, then, we can look at these erosional areas, these troughs that show the high-res version of the layers, and to try and get some more information about the timing of things. So one way that people do that is they look at the brightness of these layers. So we take an image from one of these troughs, and if I put it on its side here, you can see the layers have bright, dark variation, and we can figure out or connect those bright, dark variations with orbital variations that we saw in those other plots to try and get an idea of when the timing is. So there's pros and cons to that. It turns out the bright, dark variations might not be connected to the properties of the layers at all. When we came along with high-rise and high-resolution images, we saw these exposures of the layers were covered with dirt, and you can see even the dirt is kind of slumping downhill in places. So it's not really clear what the bright, dark stuff means at the moment. The other way to do it, which people here at U of A did in the Becerra et al. Paper a couple of years ago, they took these high-rise stereo DTMs and profiles along these scarps. And this is the elevation profile along the scarp here. And if you zoom up, you can see these individual layers are just like little bumps here like that. So instead of plotting the elevation, we're going to plot just the bumps. And then you can see these layers kind of moving or changing with depth in this other kind of plot, basically just looking at how much they protrude out of the scarp face like that. So now we have something that looks like a record with depth, and we have the insolation changes or the sunlight changes with time. So with that record with depth and with that other history of Martian orbit change with time, we can try and put those two things together to date the layers. It didn't turn out to be quite so simple, unfortunately, because the connection between the orbital variations and the climate is not 100% known. So we know how the orbit varies, but we don't know for sure how that affects the climate. This is a little fuzzy, but we can use models again to try and figure out how this works. The Earth models work very well, and because Mars is similar to the Earth, we can hazard a chance that we'll be able to do this on Mars. So I'd say this is fuzzy, but it can be simulated. Even if we understand the climate, it's still hard to connect that to the layers that we can measure, and I would put this in the category of just plain fuzzy, but there's a lot going on here that is influencing each layer. So this is just one picture on Mars today, but it shows this water ice baroclinic cloud with all these waves coming off topography that's creating the cloud here. There's a dust storm right here at the edge of the polar cap. This is carbon dioxide frost that will probably go away later in the summer and so on. And in cartoon form, I won't read off all the things here, but there's a lot of different things that are influencing the climate here. So these fuzzy cloud-like areas still need a lot of work to try and connect these things together. But there are models that have done this in a simple kind of way, and it's maybe not the final answer, but it's something that is probably very close to the final answer. We were able to use these virtual ice cores, these transects of how the layers behave with depth like this to validate these models. And they show how the accumulation rate of ice varies with depth, and the accumulation rate of dust varies with depth, and how the dust to ice ratio varies. And you can see the dust to ice ratio, or how dusty each layer is, gets higher or lower with time. And this is probably what is causing the layers to protrude out of the scarp front or to be flat with the scarp face with time. So there's a lot going on here, and certainly requires a lot more work, but I think with high-rise and those stereo DTMs, we've managed to take the first steps at least, and that now we can assign ages to all of these layers here. And the next step will be to figure out what those layers can tell us about the climate at that particular time. Okay, so to sum up a bit then, I think Mars can be this really interesting bridge between the extrasolar planets we're about to discover and the very well-studied Earth that we know and have all these advanced techniques that we can bring to bear on studying. We know a lot now about how climate and the ice deposits on Mars vary much, much more than we knew about 10 or 15 years ago, and that's mostly because of MRO and instruments like this radar and the high-resolution camera data that I showed. The data on the layering that we have is still pretty coarse, so the radar instrument's pretty low resolution, and the exposures that we look at with Highrise are still covered in this dirt layer, so they're hard to interpret. But we're doing much better than we did. And we still don't have the sophistication in the modeling that we have when we're studying the Earth, but that is also improving. So there's definitely more missions needed to find finer scale layering, to look for ice in other parts of the planet that are connected to the poles, like that layered mid-latitude area that I showed, and also landed missions on the polar cap to like physically sample some of these layers and extract more climate info. And then the final conclusion is that Highrise is pretty awesome. So I've showed just one area of research and how Highrise has contributed to it, but this is being basically the story across all different types of research on Mars, from impact cratering to volcanoes and to the action of rivers and so on ancient Mars. So the future of Mars exploration is pretty much just centered around sample return. I'll just spend a moment describing this. This is inside our last lander here. MRO is back here. Back here. These are all slated to launch in 2020. So there's a United Arab Emirates mission, a Chinese mission, a Chinese lander, a NASA rover, and a European rover. And then beyond that, it's all about sample return and getting samples back from Mars. So our 2020 rover is supposed to collect these samples. So none of this is particularly helpful for studying ice in the polar regions, but we do have one opportunity that Ali and I are involved with here, and that is to apply to a mission of opportunity program that NASA has. So we are proposing a mission to study these ice layers and terrestrial planet climate change using higher resolution radars and other instruments to study the climate. So this is under consideration by NASA now. So hopefully I'll give a talk in a year or two and you'll get to know much more about this if it's selected. And I'll just finish up by saying one more thing, which is that Highrise takes and appreciates suggestions from the public on how to, or what areas of Mars to take pictures of. So you can go to uahighrise.org, click on High Wish, and you can pan around the surface of Mars and you can select targets and enter your rationale for why you want to take that. And then you will receive an email later on if that is successfully acquired. So because of the seasons on Mars, some targets take a long time to acquire and so on, so you might not get that email for a long time, but we definitely appreciate the targets. So with that, I'll just pause and take any questions that you might have. Thanks.
Do we have any questions? We're going to be passing around microphones, so please wait and talk into the microphone to ask your question.
There is a difference in gravity between Mars, Mars and the Earth. Is that taken into consideration when you're making decisions and predictions about formations on Mars?
Yes. So for these ice deposits, the main influence that has is how fast they flow. On Mars, it appears those polar caps aren't flowing at all. Like the internal layers are completely undisturbed. Whereas if you look at internal layers on a terrestrial ice sheet, you'll see some disturbance from the flow. But it seems like the low gravity and the cold temperatures on Mars are limiting how much the ice can flow, because it just doesn't have the weight to squash itself flat that terrestrial ice sheets do.
Bueller. All right, surely there's got to be more questions. We just saw like amazing resolution images of Mars. Who wants to ask a question? Yeah. Let's do it in the microphone.
How long is your equipment designed to last for yet?
Oh, well, that's a great question. Its warranty expired a long time ago, so it's still going. It launched in 2005, and it's already lasted almost as long as the last object to function in space has. Our NASA has told us that we're supposed to stay alive until 2028. And I don't know how we're supposed to do that, you know, if something goes wrong. But yeah, that is their instruction to us, and that is based around trying to support the sample return effort and take pictures of the things that are on the surface. Yeah.
Somewhere I heard news somewhere that when we're going to Mars here shortly, using the moon as a stepping stone.
Yeah.
I'm down here. Can you help me understand that?
Yeah, I mean, that's sort of difficult to understand for a lot of us. So the plan is that the moon will be a kind of training ground, I guess, for operating in space and for astronauts to practice operations on the surface. But yeah, so this is where this phrase like the moon is a stepping stone to Mars comes from. But you know, my own personal view is that it's not super useful, that we should just go direct to Mars, I think.
So to play devil's advocate, I think if something bad happens, I'd rather be 3 days away from home than 9 months.
Yeah. If something bad happens, you're
screwed anyways, so.
Earlier in your presentation, you mentioned that about 64,000 images were taken, which is about 3.5% of Mars. Can you explain the process in choosing those locations?
Yeah, sure. So we have a science team that span lots of different disciplines, and they all make suggestions. And we have this public suggestion tool where we get an additional source of suggestions from. And we have people who prioritize all these suggestions, and then we plan the observations in 2-week blocks. So we get an orbit file from JPL that tells us where the spacecraft's going to be, and that tells us which of the suggestions we're able to see. And so then we get a big list of all the things that are potentially viewable, and we look for the highest priority ones in that process and kind of knock those out. Some areas are really hard to get images in because they're super popular. So like Valles Marineris is like very popular. Everybody wants a picture in Valles Marineris. So it's very hard to get one of those. But because it's a polar orbiter and all the orbit tracks go over the pole, getting a polar image turns out to be pretty easy because we got lots of opportunities every 2 weeks to do that. The only trick is it has to be daylight because it's a camera. If it's winter time, then you have to wait half a Martian year, which is like a whole Earth year to get your picture.
Or you can do your dissertation on the Kansas of Mars and get as many images as you want, because everyone's like, why are you taking images of there? Because it's flat and boring. But it's not flat and boring.
Sorry. So the spacecraft that's got the 3-meter antenna, I'm right here, sorry.
Oh, there you go. Sorry, yeah, I couldn't see.
That was the Reconnaissance orbiter,
Yeah,
right?
so that's the one that Highrise is on. So
right. So are spacecrafts in the future going to have like even bigger antennas than that?
Yeah, probably, because we just want more and more data all the time. And the way to do it is actually sort of what we're proposing in this other mission is this antenna here, you can kind of see through it. And that's because it's a deployable mesh. So 3 meters, we're kind of maxing out what you can do with like a fixed solid antenna. And in the future, I think a lot of these spacecraft will have antennas that unfold, and it'll just be like a mesh that can be used then.
Do we know what causes the lava swirls? And I don't believe we have that phenomenon on Earth, do we, lava swirls?
There are lava swirls on the Earth, but I have to admit I don't understand the mechanism by which they're made. So I'm sorry, but if I get your email address afterwards, I'll follow up and send you an explanation. Yeah.
Is there a general scientific consensus that liquid water was on Mars at one point?
Yeah, definitely. Early in its history, like in the oldest areas on Mars where those rocks are really old, we see huge river channels, and we see evidence like of smaller meandering rivers and so on. In recent Mars, and I mean recent from about 3 billion years ago onward, it's been in this cold and dry state, and liquid water has probably been extremely rare. So those streaks that I showed moving downhill are kind of like the best evidence for liquid water right now, but they're still argued over and may turn out just to be completely dry phenomena. Yeah.
I got a question.
Yeah.
So on your High Wish website, have you had anything that was like really strange as far as somebody requesting?
Oh, yeah, so many Face on Mars requests.
One that stands out.
Yeah, so I don't think there are any that stand out above the others. So yeah, the Face on Mars was a popular one, but we've taken lots of pictures of that, and then the other one that rarely gets taken is people saying, you know, because this is where my house is on the Earth. So they go to the same latitude and longitude as wherever they live, and they ask for a picture. Yeah. So if you're going to do that, just make up some other reason. Just create some other justification so that you get your picture.
Any remaining questions? Going once? Going twice? All right. Thanks for coming, everybody.